Hello.
Hello guys, nice to see you. How are you doing?
Fine, thanks.
Good. Good afternoon, everyone. Yeah, I'm also doing okay. Thank you. So last time we started to discuss the mechanism of heat, like energy transfer in the form of heat. So first one, which we discussed already, was heat conduction. When we have some material and two sides of this material are at different temperatures because of heat conductivity of this given material, there is and temperature gradient, there is certain energy transfer between these hot and cold surfaces. So the second mechanism for energy transfer is called convection. So the basis for this phenomena is the fact that warmer parts of usually it's gas or liquid, they are lighter than colder parts. And because of different weight per unit volume, what happens that if we have, for instance, some hot surface underneath and cold on top, so we heat up some volume with water or gas from the top, this gas next to the hotter surface thermally expands, it becomes lighter and starts to move upwards because colder air or liquid, gas or liquid, pushes it out from this bottom region because parts of liquid is colder and subsequently it is heavier. So eventually we get such a circulation of cold and hot regions of water or gas, and that is additional mechanism which also facilitates the heat transfer. So keep in mind that we still have this thermal conduction. If we have, for instance, some liquid, it possesses some thermal conductivity, and we do have thermal conduction. However, on top of that, we also have contribution from convection, which could be even more, could be much more sufficient. So it depends, of course, on the properties of material, but for instance, thermal conductivity of gas is quite low because low densities molecules are far away from each other, they interact not so intensively. And convection, in that case, will be the dominant mechanism for energy transfer. So one more option for energy transfer, maybe it's also good to highlight with this convection that in case of the absence of gravity, this mechanism doesn't work because then it doesn't matter what is the density of warm or cold parts of the liquid or gas. If there is no gravity, there is no weight of these warmer and colder parts, and nothing causes this convection motion. So that for sure requires presence of gravity. However, so far we were talking about heat transfer in case when we have some medium. So we have some material which provides opportunities for heat conduction, or we have some gas or liquid which on top of that provides options for convection. However, what if we have hot and cold surface and there is nothing in between, so there's vacuum? So do you have any ideas how heat could be transferred in that case? So no heat conduction, there's nothing in between, so heat conductivity is equal to 0. No convection because there is nothing to circulate in between these surfaces. However, there is still a mechanism which can provide opportunities to transfer energy between such surfaces. Any suggestions on this mechanism? If you put your, let's say there are such types of heaters, so-called infrared heaters, when there is a filament of nichrome with some metal alloy of nickel and chromium, which doesn't burn in air because of its native oxide protection. And when we run currents through such filament, it becomes red. So it actually heats the room where we put it with infrared rays, with radiation in the infrared spectral range. And you can feel it immediately, so you don't need to if you have some convector which heats because of just hot surface, then you need to wait until this convection happens and hot air spreads all over the room in order to feel this heater is working. But in the case of these infrared heaters, you feel this heat immediately as in the same moment when you turn it on. So other thing that you get cold if you switch it off immediately. But that's kind of an advantage to quickly warm up if you have an option to use such infrared heater. So obviously the third mechanism is radiation. It doesn't require any environment. It can happen in vacuum. Actually, it always happens. All bodies irradiate. And there is so-called model radiation of black body, absolutely black body. So there are equations which describe this radiation. We will write it down when we switch to the slide mode. So we will not go into details how it works, because that is the topic which will be covered in like future semesters for general physics. But here we need to highlight that this is a mechanism for heat transfer, which is possible, and everybody radiates. Depends the spectral range, spectral composition of this radiation depends on the temperature. So you can use some infrared vision in order to identify human beings or some other alive warm blood organisms. They are hotter than background environment. So by this contrast, you can, with quite high accuracy, identify their presence. And if you have hotter objects, then this radiation is shifted towards shorter wavelengths. And when we warm up some surface, let's say some metal up to 500 degrees Celsius, it starts to already radiate enough in the visible range, in this dark reddish color, that we can identify it visually. So we don't need to rely on some instruments which can detect infrared radiation. But we can already see at 500 degrees Celsius, we can already see that the surface start to irradiate in red color, which is noticeable. So if we increase temperature further, this red color becomes like brighter, and eventually we can get to, if we get to very high temperatures, like something what we have in this incandescent filament light bulbs with like Wolfram filament, then we can reach up to 1400 degrees Celsius, and there, in that case, they already glow with something close to white light. Still not white, but it's definitely not red anymore. So it's like becomes to shifts towards shorter wavelengths, and that's how we can use it for illumination of our living space or streets. So that is an option, the third mechanism for energy transfer, which along with thermal conduction and convection. Okay, let me switch now to the slide mode. Oops. One second. It didn't work initially. Now it works good. One more comment on this radiation transfer of energy via radiation. So power means energy per unit time, like heat per unit time, which is transferred, is given and can be calculated by using the following equation. So we have sigma times A area, then we have E, which is emissivity of the surface, so it depends on the surface properties, and we have temperature in the power of 4. So this sigma is a constant. Its value is 5,669 10 to -8 watts per square meter Kelvin square, Kelvin in the fourth power. And so A stands for area, E stands for emissivity, means actually emissivity for this absolutely black body. It is emissivity is equal to unity. Why? Because absolutely black body can absorb all wavelengths, so it doesn't reflect anything. Means if it can absorb everything, it can emit also in all spectral ranges. So that's the rule. If you want some surface to radiate in certain spectral range, you need to be sure that it can absorb in this particular spectral range. And obviously, radiation power, like energy per unit time, will be higher for materials which can absorb, like surfaces which can absorb in broader spectral range, because they can also radiate in this broader spectral range, means more energy can be dissipated via this mechanism. So this emissivity defines the features, the property of the material surface. The black surface can radiate more than white surface. Okay, so with this we discussed the basic features of this mechanism: conduction, convection, and radiation. And now we can make next step and start working with the relationship between these known macroscopic parameters which describe state of ideal gas, means for instance pressure and temperature, with some microscopic fields of can describe motion of individual atoms or molecules, those which create this ideal gas. Okay, so that's our goal, main goal for today, and we need to consider certain conditions which we will stick to while we derive our equations. So first of all, we deal with ideal gas, and we need to consider now some so-called molecular model of ideal gas, means kinetic theory. So the number of molecules which form ideal gas should be large, and the distance between these molecules or atoms should be always much larger than their dimensions. So we can consider that dimensions of atoms of ideal gas, they are negligibly small. We consider them as mathematical points. And molecules obey Newton's law of motion. But as whole, since we have many these atoms or molecules which form ideal gas, they move randomly, so in all directions with equal probabilities. Molecules interact with each other only via collisions, so there is no other form of interaction. So when it just freely flies, it does not experience any interaction with other molecules, only in the moment of collision. Molecules make elastic collisions with the walls of the container. That's an important statement. So when a molecule hits the wall of the container, it interacts elastically with this wall. And the gas is considered as a pure substance, means that all atoms or molecules which form the gas they are identical. So we don't have any impurities there. Okay, I guess that now we can clean this part. We don't need it anymore. And now with considering all these statements, we can make our efforts to find the relationship between such microscopic variable, like state variable as pressure, with microscopic quantities that describe motion of molecules which form the ideal gas. For this purpose, we consider n molecules, and they are in a container with volume V. The container is some cube with the side D. So let's have a system of coordinates. We have X, Y, Z, and we have our cube. So our cube will look like this. Okay, so inside this cube, we can consider at the beginning just one molecule with mass m naught. And it moves with certain velocity vector v. So now let us first consider a projection on axis x, and then we will apply this all these concepts for other directions. So now we are interested in Vx. We can put it Vxi as one of these many molecules, its velocity projection on axis x. Sorry, 1 minute, please. I need to answer. There's a call I need to answer to this related to equipment delivery. Just 1 minute and I will come back. Okay, I'm back. Sorry about this. So now we need to consider the interaction of this molecule with the wall of the container. So we can write it here, like draw it. This is the wall of the container. This is our molecule. Then we have velocity vector. We have projection Vx I, and then we have also another projection. Let's say it's Vy I, interacts elastically with the wall of the container. Then we have this molecule already reflected from the wall of the container. And this is its velocity vector. And here we have projections, Vxi and Vyi. So what do we see here? That in terms of like the momentum before the collision and after collision in the x direction, we can write that we have m naught times Vxi. This is momentum of this molecule before collision. And then after collision, since it's elastic collision, it is reflected in the opposite direction without change of the value of this Vxi. So it will be minus m naught times Vxi. So now we want to find the change of the momentum. That will be delta p xi. So in the direction of x is x for this particular single molecule. And that will be equal to minus 2 times m naught Vxi. So why minus 2? Because we have here minus m naught Vx I, which is momentum after collision, then minus m naught Vxi, which is momentum before collision. So we eventually end up with minus 2m naught Vxi. So we remember from definition of linear momentum that we can express it as some average force acting on the molecule times delta t, which is interval of time during which this collision happened, or lesion. So that is called impulse of this force, and that is equal to the change of linear momentum delta p xi, which is equal to minus 2 m naught times Vxi. So Fxi is some average force in this direction x, which acts on the molecule. However, this interval of time during which collision happens is very small, and you cannot accurately define it. So what is helpful in this situation we need to consider that in order this molecule to hit the same wall again, the molecule needs to travel along x direction, distance 2d. So from this wall, it has to move here and then back in order to hit it again once it already hit it. Because it's reflected, so it has to travel. So here is the side of this cube, which is d. So it has to travel 2d distance in order to hit it again. So means that we have one hit of molecule. During this time, it has to travel distance 2 times d. So in this case, let us figure out this time interval, delta t, which will be 2d divided by vxi. So that is time interval along which molecule can hit the given surface only once. So if that is also the taking this into account, we can average the force during collision over the time interval delta t now, not delta t collision, because in any way we know that during this longer interval of time, there will be only one collision. So we can average it per this time. So then we have some average force Fi, which acts on this Fxi, which acts on this molecule, times already delta t, not delta t collision. And that should result in the change of the momentum of this molecule, minus 2 times m naught Vxi. So, and V xi now is average over the interval of time delta t, which defines the time the molecule has to move, like fly distance 2d in order to hit this wall again, and then we can extrapolate this average for some long-term average, but doesn't matter for us because we can just normalize per single hit of the wall by this molecule and consider the interval of time during which it will not physically be capable of hitting this wall again. So now we can define this average force, and let's call it Fi, just without x, and that will be equal to minus 2m naught Vxi divided by delta t. Since delta t is defined, we can now substitute the expression for this delta t into our equation. So that will be minus 2m naught Vxi. Here will be 2d times Vxi. That is equal to minus, so 2 and 2 will cancel out, Vxi squared we will get. So that will be minus m naught times Vxi squared divided by d. Okay, so we have this. We can maybe write it on the next slide to have it. So F I average will be equal to minus m naught Vxi squared divided by d. So taking into account the third law of motion, by the way, what does it state? What is the statement of the third law of motion? Third Newton's law. Yeah, we have reaction force, which is equal by magnitude, but opposite in direction. So that's why this is force which was acting on the molecule, but we are trying to calculate pressure, and that's why we need to consider force which molecule exerts on the wall of the container. So that's why Fi average, let's call it wall, and that is equal to minus Fi average, and then it is equal to m naught Vxi squared divided by d. So with this in mind, we can calculate now some average, total average force, F, which exerted by the gas, so by all molecules which forms this gas on the wall, and that will be the following. So we will need to sum I is equal to unity from unity to n, total number of molecules, times here will be m naught Vxi squared divided by d. And we can take out from this sum m naught actually, yeah, we can keep it. So taking into account that all molecules are the same, so we made this statement of the purity, we can actually write that here will be m naught divided by d, sum for I equals to unity times n until n for all molecules Vxi squared. So now we want to get some average. In order to proceed further, we need to express the average value of the square of the components of x component of the velocity for n molecules. And the average will be Vx square average. So we need, how we get average? We have sum for all Vx I for all molecules, and then divided by the number of molecules. So we can write it as follows: I equals unity to n Vxi squared divided by total number of molecules n. So with this average for all molecules Vx squared, we can express now the average force as m naught divided by d times n times Vx square average. So instead of this sum, we can put now n times Vx square average. V times Vx square average. So that is important because we don't know velocities and projections of these velocities for each molecules in this direction, x direction, and that's why we want to deal with some average values. So once we have these four average force exerted in the direction x, we can also define in all other directions. So for that purpose, we consider again a single molecule with velocity component Vxi, Vyi, and Vzi. So we can write that V of some molecule Vi, Vi square will be equal to Vxi square plus Vyi square plus Vzi square. So we have components of this velocity vector, and the average for velocity is also can be written also in the same format. So we will just operate with average values. So here it's already not I, it's average, square average plus Vy square average plus Vz square average. So it is important to go from definition of average velocity x component to just average velocity, because we don't know exactly how they are. They are randomly moving, but we need to specify something more reliable and clear, which can have a clear relationship to the temperature, for instance, and that is total velocity of this molecule, not its projection on different axes, because they are not defined well. So taking into account that we have random motion, that implies that Vx square average should be equal to Vy square average, and that should be equal to Vz square average. Because we have random motion, we have equal opportunity to move in these molecules in any direction. So taking that into account, that they should be on average, we're not talking about given molecule, but on average, they should be for this large number of molecules, and they should be equal. And then we can express that V square average is equal to 3Vx square average, because we sum up in all three directions, so we get 3. And from here, we get that Vx square average, which is used in this equation for average force on the wall. We can express now this force in terms of velocity, not in terms of its projection on axis x. So average Vx square is equal to V square average divided by 3. So now we substitute, instead of Vx square average, its expression, and we get the final expression for the force which acts on the wall of the container. So that will be 1/3 times N times M naught V square average divided by D. So that is the equation which defines the relationship between average force and velocity of these molecules. Now we keep this in mind, since we don't have more space here. We will write it on a new slide. So that will be, what do we have it here? 1/3 N. Okay. F is equal 1/3 times N times M naught V square average divided by D. And in order to get the pressure of all molecules of ideal gas, of all gas on this wall, we obviously need to divide this force by area. And area of the wall is D squared. So now pressure is equal to this force divided by D squared, and that is equal to 1/3 times N times M naught V square average divided by D cube. And D cube is nothing else as volume. So D cube is the volume of our container. So we can write that will be 1/3 of N divided by V times M naught V square average. So now if we multiply and divide this expression by 2, so we can get the final equation for pressure in terms of microscopic parameters, mass of the molecule and its velocity. P is equal to 2/3 N divided by V, and here we can write M naught V square average divided by 2. So it's actually kinetic energy, average kinetic energy of a molecule in ideal gas. So this is the relationship. We will get higher pressure if we have more molecules, and also higher pressure if we get higher velocity, speed of these molecules, specifically speed of molecules in second power, so it will have stronger impact on pressure, and less pressure if we increase volume. So with this, we finish our discussion today. We provided this derivation of the relationship between pressure, macroscopic state parameter, and microscopic parameters of the kinetic parameters of ideal gas. Next time we will continue further and find the relationship between another macroscopic state parameter, temperature, and this microscopic parameters of which are called kinetic parameters, speed and mass of molecules. But that will be our next discussion. First, we are done now with the relationship between pressure and speed of mass and speed of molecules in the ideal gas. Okay, thank you very much for your attention. Any questions? Okay, thank you again, and see you next time on Friday. We will finish this consideration of the kinetic theory of ideal gas by introducing the relationships between temperature and speed of molecules. Okay, if everything was clear, then have a good day. Take care and see you on Friday. Bye-bye.
Thank you.
Bye.
You too.
Thank you.